This is IAT 355, Lecture 12.2 on the multiple views topic. So what we're going to do is continue our conversation about what to do with too much data. And we're going to speak now about facets, which is taken from Munzner's book, Chapter 12, in particular, the section called faceting, which is her term for, given that there's too much data, one of the things you can do is to deal with allocating some of that data, or some of those cases, or some of the something, partitioning it, partitioning the screen real estate, and how that partition of the screen real estate interacts with the partition of the data set. Okay, so that's what facets is about, generally speaking. So, what lecture segment 12.1 was talking about was for the computer graphics techniques was to attempt to create more visual bandwidth, as it were, more visual capabilities using computer graphics techniques to use the visual display instead of depicting a number of individual, say, scatter plotted points, to represent them as an accumulation of points. And the purpose of that is to get across the notion to users or analysts what the accumulation looks like. In some sense, that means to give up a little bit on seeing each individual point in exchange for the ability of seeing a huge number of points at a particular location. And so in some sense, that is a commitment. Those kind of techniques are a commitment to doing overlay. That is to say, overlaying point after point after point, drawing point after point semi-transparently, or with the FlowJo accumulation thing, rendering to a floating point region, and then doing contouring on that regioning and rendering that contouring. In any case, there are a number of ways in which you can deal with the fact that there's too much data. So one of the things that you can do is to think of the rectangular region that you're drawing in. Let's assume, for the sake of argument, that is fixed. You're stuck with, say, a 2K display or a 4K display, whatever it is. I mean, it's great to have 4K, but it's still limited, strictly speaking. It's 4K. It's not 5K just when you want it to be. And so if you're got that limited amount of screen real estate, or a limited amount of visual acuity to be able to read all that screen real estate, there's a number of things that you can do. The graphics techniques essentially try to use each pixel better, using transparency and other kinds of computer graphics tricks, by overlaying. Another thing you could do is to basically say, tell you what we're going to do. We're going to draw a picture in this, a region of the screen that is dedicated to my visualization, and I will draw, a single visualization in one area, and when I need to draw some other stuff, I'll replace that image, that visualization, with another visualization. And so, I drew scatter plotted points first, and then I decided, no. What I want to do is I want to do a parallel coordinates plot of the same data, say, for the sake of argument. And so what that technique does is it asks you, the analyst, to rely on your own memory. And what that really means is that it relies on your image memory, which, is always going to be subject to change blindness. Or for you as the analyst to be carefully taking notes about your process, or taking screenshots, or using some other tool to manage the fact that one image is being replaced with another. So that's what's going on with the always replace thing. You could, in fact, always replace one image with another. And what that does is it puts a cost on you, the analyst's memory. Another choice is to say, okay, no, what we're going to do is we're going to take those 4K pixels, let's pretend the entire region is 4K, and what we're going to do is, because we have a number of variables, we're going to cut up the space. Let's say there's 10 variables that you want to plot. What we're going to do is to cut up the space into 10 equally sized segments. Let's pretend that that's going to be pleasant to look at. And each of those 10 regions that are distinct on the screen, I'm going to plot some information. I'm going to plot each variable in each of those 10 areas. So area 1's dedicated to variable 1, plotted against something. Area 2 is dedicated to variable 2. Area 3 is dedicated to variable 3. Now, if you have 10 variables, that's fine. And we'll show something called a scatter plot array, which is that technique, plotting variables against variables. We'll see that shortly. But the problem with that is that it takes too many windows. So, instead of one big display where you have to remember stuff, you have a whole bunch of little displays or smaller displays where you can see everything, but every single thing that is plotted to some degree is plotted, multiple times. You have to do the same plot multiple times, except it gets less pixels. So, it's not quite a wash as a trade-off. But then you have to guide your attention to the piece of the visualization that you want to pay attention to. And so it's transforming a memory technique into an interaction exercise for the user. And, that's fine. It's the cost of doing business. The other technique shown on the right is something called Facets, which is to get inside the data set a little bit more and interactively reorganize the way in which plotting takes place so that you can interact profitably with what's going on. And we're going to talk about those techniques right now. Okay. So the idea with facets, it's a general term that Munzner's using to get across the notion of splitting the data and or dimensions. It could be data or dimensions, or perhaps both, as long as you're very clear about which one you're doing, and splitting them into multiple coordinated views. The most important element of that sentence is coordinated. It's not like there are separate pieces of paper. It's an interactive visualization. And one of the primary things that you have to do is when you interact with one part of the display, your interaction, as long as it's not just the mouse moving around on top of the visualization, interactions with one part of the display about a data element, if that data element is also visible in another part of the display, both of those elements, when one is selected, the other one needs to light up too. Okay, so that's absolutely essential for this kind of suite of techniques to work. And so here's an example on the lower left from the University of Maryland, in which there's a scatter plotted on top of the geography of central Maryland around the Baltimore area, a bunch of scatter plotted points indicating incidents, and down below is a parallel coordinates view of the same thing, where each of the incidents is a polyline. And as you can see here, just a little bit not so clear and super salient, they're using the transparency technique that I'd spoken of earlier. These are no longer standard single pixel width polylines. They've been drawn with transparency, and you can see that there's an accumulation, particularly at these locations, which are discrete variable values for, say, nominal data. And so the idea is to plot these things twice in separate views, and perhaps have a different representation in each of the views, or a representation that shares something in common. And so spatial location is in common on the right. So here we have, again, this is the Maryland area. That's Chesapeake Bay. That's Maryland. I guess that's central Pennsylvania. And this is plotting water quality and fertilizing technique, manure versus fertilizer. The geography is the same, and what's being plotted is the intensity of a particular agricultural practice. So faceting is just kind of this general term for splitting up, in some ways, the data or the dimensions that you've got in coordinated views. So you have a bunch of choices as to how to do this, and Munzner lays these things out. So one of the things you could do is to share the encoding and have that encoding be the same or different. And one of the key things that's important is, as I said, is linked highlighting, what Munzner calls as a generic and general term. And I think it's actually kind of a useful one, linked highlighting. It's also known as brushing. That is to say, you put your cursor on one data point, and that data point gets highlighted everywhere that it's visible in the visualization. The encoding in those multiple views could be the same or it could be what she calls multiform. That is to say, it's one representation in one view, a different visual representation in another. Say scatterplot versus parallel coordinates versus bar charts. Three views, all of the same kind of data, but different representations. And each of those representations has the job of helping you visually understand things in a different way because of the strengths and weaknesses of each of those visualizations. So that's splitting up the view. Another thing is to split up the view, but what you're doing when splitting is you have you're splitting also the data. So this is a very important point. It seems a little subtle. Visually, it's hard to tell that there's a difference between these two things. But where you're splitting the view, the intent is the data set that you got going is in every window. In splitting the data set, what you're doing is one chunk of one distinct subset of the data is in view 1, a different distinct subset is in view 2, and a different distinct subset is in view 3. Let's say there's 3 views. So it could be the same data set everywhere. It could be different subsets, or what's called small multiples, and we'll get into that. The other thing to do is to do a spatial layout of views such that the coordination between the views is geometrically sensible, and we'll show what that means as we move forward. Finally, the last thing you can do is to just simply pile things on top of each other, which gets you back to the computer graphics techniques that we spoke of earlier. The computer graphics techniques are effective, but what that's doing is, at the end of the game, let's say you've selected the data you want to look at, you've thrown the rest out for whatever reason. Let's say you only want to see Eastern Conference of NBA. I don't know what kind of data you want to look at, and you don't care about the Western Conference or whatever. Forgive me, I don't know NBA techniques, the terminology. And you're only focusing on the East, and that's what you want to do. Given that you've filtered out or removed the non-Eastern Conference stuff, you can then focus on that stuff and layer one plot on top of another. And that's this last thing, superimposing layers. And she's shown the little illustration of, here's one plot, here's another one, and those things are plotted together in the lower right. So she points out that there are a couple of dimensions, if you will, speaking at the higher level abstraction, a couple of directions along which you can split the task. The first is splitting the data, and the second is how you split the encoding. So there are two things that say the word that have a big slash through the middle. So if you have all of the data and it's the same encoding in every window, then you're plotting the same thing twice, so that there's no gain or loss there. Well, there's loss of pixels, but you haven't, you're not accomplishing anything. There's no value added in doing that. Similarly, on the right, if you have no data and different encoding, it's completely different data, completely different encoding. You're just using the screen pair of screen areas or multiple screen areas to plot completely different data sets. So there's no linkage. And so that isn't, the splitting of the display where the data is completely different from one image, one view to another, that your plot, you're just essentially doing visualization. Your left eye is paying attention to one and your right eye is paying attention to the other. So there's no linkage there. Where the interest really is where these two sort of, end cases are not in play. So taking all the data, right, in this left column and having different encodings per window, this is what you end up with when it's a multiform display. So here, it just, for example, is shown a bar chart of some of the data and a scatter plot of the data. And that's what Munzner terms the multiform. If you have a subset of the data and the same encoding, so this row here, two separate windows, but the subsetting operation is the subset has more data in one view and less data in another, then what you've ended up with is an overview and detail plotting technique. And we see this, in map visualizations. You see it in video games with the sort of the map and the HUD part of, the HUD heads-up display segment of the display screen in a first-person video game. And in older versions of Google Maps, you could see the overview, which is very small typically, and the detail, which occupied the vast bulk of the display. And Munsner gives that example in her book also. Where you have different subsets and different encodings, you end up with multiform and overview detail. So you might use the overview, which you would imagine typically is smaller, but it doesn't have to be, as a navigation technique. Let's say you're doing geography, but what you really want to do is use that geographic overview as a selection mechanism to say, show me all the Starbuckses, and then all the Starbucks data, somehow or other you magically get that, and you're doing scatter plots of whatever you want to do from the Starbucks sales data for whatever. So that's multiform overview and detail. On the right here is where there is not the same data in each view. In fact, there are different data in each view and the same encoding, but the idea is, this thing is called small multiples. The idea with small multiples is that distinct subsets of the data are represented in different segments of the screen, but the intent is they're all part of the same data set and they're all closely linked. Okay. So here's an example of multiform, which is same data, different encoding. So here is a bar chart of some data here, and that's industry, psychology, empty units, foreign ownership, etc. So this is a real estate database. Okay. And so this is an analysis of property buying and selling. And so these are the overall factors, right, being represented as a bar chart, and each bar represents a different kind of cause and effect. And over here on the right is, a tree map of the same data. So it's a different encoding on the right. The notion with the tree map over here on the right, of course, is you're taking the data set and subdividing it and subdividing it. This is squarified. There's a big division line to start the process here, and then within that, the orange stuff versus the blue stuff, and you can see the relative importance here. This thing works reasonably well because there's not a huge amount of hierarchy in the tree map. But in essence, it is getting across two different aspects of the same data, and that's a multiform visualization. And of course, what you're doing is you're splitting the screen into two separate pieces: the stack bar charts on the left, and the tree map on the right. And each are emphasizing different aspects of the display. And you can see here, although it's reasonably clear from this, that the orange and blue regions are the same size pretty much. With different subdivisions. Here's another variation on this. Here is sort of business kind of data. This is a timeline, right? And what's being plotted is a year's worth of data in each of these lines, and it's separated by color, and there's not a link mark drawn from the end from say December 2011 to January 2012. The tick marks are a little bit unusual. They are determined automatically. So this is from Tableau, of course. On the right is a different, so these are plotting totals, say, right? Total income or something. And on the right is, a number of Tukey's hinges plotting each individual month's worth of data, right? Each week, actually, worth of data, and the distribution of the sales information as individual data points, but they're being plotted into these Tukey's box plots here, which have been enhanced with color. Okay, so here is another one of these things, and this is the iris data set. Again, what we're doing is doing scatter plots, but this is a scatter plot array in which a very simple one, in which this is petal length, and so that dimension is common here along the bottom, here, and here's sepal length here, and here's sepal width. This dimension is common here, and petal width. This dimension is common here and here. Okay? So that's an example of a scatter plot matrix. And basically what a scatter plot matrix is a slightly more organized version of taking every pair of variables, plotting a scatter plot. And so what that means is if you have n variables, you end up with an n by n array of scatter plots. So that means you have to do the machinery has to do a lot of scatter plotting. And along the diagonal, you plot a variable against itself. So here's miles per gallon plotted against miles per gallon. And you end up with a diagonal line typically. For some variables, of course, you end up with a dense a suite of scatter plotted points, and you can learn just a little something about the kind of their distribution, the density of information along that dimension. But you have to rotate your mind by 45 degrees. And so what that gives you the opportunity is to see how miles per gallon, say in this case, is plotted against cylinders, horsepower, weight of the car, acceleration, year, and origin, national origin, Japan, Europe, USA. And so what that enables you to do is to see clusters, trends, and correlations, fairly readily between pairs of dimensions. People do use this, and this FlowJo thing that I mentioned does this scatterplot array thing, except it does this accumulation because it uses millions of points. And what a practiced user of these techniques does is really learns how to construct in their mind what the higher dimensions are doing and how they're interacting. Really, what you're seeing here is pairwise interactions of the data along pairs of variables together. Here's a slightly more elegant layout of the same thing. What we're doing is instead of putting all the labels around the periphery, put the labels down the diagonal because it's strictly redundant. Plotting itself against itself doesn't really add too much information. It doesn't add nothing, but it does add a little something. And this is where particularly you don't want to spend space on something. Also, strictly speaking, a scatterplot array, you don't need one of the either the upper right or the lower left rectangle. You don't need them unless you do want to see A plotted against B and B plotted against A. It might be instructive if you're thinking about what the correlation looks like. But you don't need that, except a triangular screen area is a little bit hard to do anything with. So another variation, of course, on this technique, moving on to the next box in Munzner's diagram, is overview and detail, and we spoke about that at some length. So here's an example, a couple of examples of overview and detail. Here's looks like financial information, and a subset here, the overview showing what that looks like. And you could also use the overview here to zoom in, and that's what's happened here. That's why you can see that this is just this region here is the entire plotted region there. And of course, you have a similar kind of thing in maps all the time. You want to know where you're looking, but you don't need the where am I in the world of visualization to be to occupy a huge amount of space. In this particular one, the overview is taking up a little bit more space than the detailed one of California, which is sort of this region here. So one of the things that Facets are doing for you, or the idea of Facets, is to you have a couple of choices. One is to take the same data set and do the same encoding. So here's overviews in detail. This plot here has been selected here in the overview, and you can see the same point has been highlighted in both displays, and the two curves have been highlighted. Over here here's the overview of Sweden, and this is the southern region, Skåne. In case you wondered, that's what that region's called. I watched too much Wallander. And here is a scatter plot of the underlying data. So a different representation, same encoding in these two views, and a different representation in the lower right. So one of the other multiform things is to, with different subsets and showing different encodings. That requires a certain amount of presence of mind when doing a display like this. And it's something that's that if you as the user keep in mind where you're at as you're pursuing your inquiries, this is useful. But one of the things that can be very hard is for other people to sort of step into the visualization and understand what you're looking at, unless all your team members are kind of always doing the same thing and always looking at the same suite of encodings. So clearly there's a geographic encoding here. There's some bar chart and scatter plot encodings, all about elements of the data. So this is profit by product. This is plotting sales against profit. This is, the product of sales compared to budget, and this is sales by month. So all of this is about commercial data, and here are the locations where the information is coming from. Okay, so that wraps it up for facets as a general concept, and that's it for lecture section 12.2.